we started out with this audio equalizer example, right? So what was the audio equalizer example? We had multiple filters in it. So if you remember, we said given an input signal, we'll pass it through, let's say, high range, mid range, and low range frequency filters. Each of them will filter those particular frequency components separately, add a gain. Okay, so there is a particular gain, and then either you attenuate it or you amplify it, and then finally add everything up. Now we know that you can construct filters using resistors, capacitors, and inductors, RC circuits, LC circuits, RLC circuits, and so on. So these are all components with which you can construct filters. Now, when we are adding the output of multiple filters, are we even sure that the output of these filters will always be in phase? Basically, what we are doing is we are adding these reactive components, capacitors and inductors, along with resistors. Are we sure that the output from these different filters, which are containing different values of capacitors, different values of inductors, they are all going to give the output in the same phase? What if they are out of phase? Then of course when we add, we'll have problems, right? Because I might be talking in one particular frequency or one particular phase, and each of the filter might give the filter output at different phase. So because when there are different phases, you add them up, the voice signal is now going to get distorted. So we want to get the output at the same phase so that we can all add them up. So how can we ensure that it's all in the same phase? Is it even happening in the same phase? Or if there is a phase difference, how to continue synchronizing, or how to even first estimate, or how to even analyze this phase difference? If we can analyze and know, okay, this is going to be the phase difference, then we can somehow compensate for it. So how to know this? Let's first see if they are in phase. If not, why are they not in phase? How are they getting affected? So basically what we are going to do is now see the effect of the resistors, capacitors and inductors in a circuit. So we'll call this by the general term impedance. I'm sure you would know that the resistor values are also called as impedance. The impedance is basically nothing but the amount of resistance that is offered to the flow of current or voltage in a circuit. So we'll say that if there is a resistor, then this is simple Ohm's law. We'll say that the voltage, this is the voltage, is equal to the current times the impedance. Okay. So the impedance can be, let's say, if you had a resistor in the circuit, let's say if your circuit was something like this. Okay, this is my, let's say, voltage source, and if V is the voltage and I is the current, and this is my resistor. Let's say this is some ohms, 100 ohms, let's say this resistance is now 100 ohms. Now, which means what is happening here, if I apply 1 volt of potential difference, then the current is now going to be 0.01 amperes. In other words, the resistance is going to oppose the flow of current in this circuit. What does this mean? So if I increase the voltage, then the current does not increase by that much amount. So if I increase the voltage from, let's say, 1 volt to 2 volts, the current will not increase by 1 ampere. Okay, I increase the voltage by 1 ampere, but the current will not increase by 1 ampere. But by how much ampere will it increase? It will increase by 0.01 amperes. So essentially, this impedance or this resistance is resisting the increase or the flow of current. So as long as the value of this resistance is greater than 1, your current is always going to be much lesser than your voltage. If you apply 10 volts, then the current you will get is 0.1 ampere. You increase that by 2 times, 20 volts you apply, but that doesn't mean that you will get 10 amperes more. So the current will only increase proportionately. So you will get 0.2 amperes. So despite applying more and more voltage, your current does not increase by that amount additively. It increases only proportionately. So this resistance offered by this circuit to increase the current or to up the flow of current is what we call as the impedance or the resistance. Okay. The interesting thing to note is as soon as you change the voltage, the current will also change. So this is always in phase. You can plug in a current source and you can change the current value, and immediately the voltage will also change. So as soon as the current changes, the voltage changes, and vice versa. So this change is in phase as long as there is a resistance. But let's say we have a reactive component like a capacitor or an inductor. Okay. Let's say that there is a capacitor. We know that the current voltage relationship in a capacitor is, I is equal to C dV by dt, or in other words, you can say V is equal to integral 1 by C I dt, right? Both are equivalent. So, but what have we written? We have written that current is capacitance time the voltage, which is exactly in this form that we have here. Like, so it says that whenever there is a change in current, the change in current does not directly increase the rate of change of voltage, but it opposes the rate of change of voltage. So here the voltage change was opposing the flow of current, but then here we don't have V or I, we have dV by dt. What is this derivative? Derivative is the rate of change. In this case, it's the rate of change of voltage. So what does a capacitor do? So if we had a circuit like this, the capacitor, when you have a current passing through the capacitor and you increase the current, the rate of change in voltage is what that is opposed by this capacitor. It is not directly the voltage. So the rate of change of voltage is opposed by the capacitance value. Remember, we had Z here. So if we had 100 ohms, then it was 100 times reducing the voltage. Similarly, whatever is the value of capacitance here, that is going to reduce the rate of change of the voltage. In other words, if I have a current, let's say you just have a current source here and then you have a switch and then you close the switch. So when you close the switch, you have a current which is rising up like this, right? But if current is immediately rising up, then what happens to the voltage? Will the voltage immediately rise up? Will the voltage immediately change? Let's say this is 10 amperes. Okay. Till this point, till 0, the voltage was also 0, the current was also 0. Now the switch was closed and immediately the current changes to 10 amperes. But then, according to this equation, the capacitor will not let the rate of change to immediately increase. So the rate of change is opposed by this capacitance value. So what would be this voltage across this capacitance? Now it will be obtained by integrating this equation. Basically, you will get this equation. So as you can see here, you have to integrate this. So let us say the capacitance value is 1. Okay, very simple. So it's minimal, it's not so much opposition. So if it is 10, then it will be 1 by 10 integral 10 ampere, from 0 to some t. Okay. So one thing to note here is you have to just integrate this. So if you are integrating it, it means that it will start at 0 and then it will start rising up slowly. So which means even though you are applying 10 ampere immediately, the voltage does not respond immediately. The voltage is slowly going to rise and then catch up with the current later. So it will take so much time to catch up with the current, okay, and then only reach this value of the current. So which means the voltage is going to lag behind. So in this case, if the capacitance is 1, then it will take 1 second for the voltage to reach 10 volts. Okay, so that essentially then that is dV by dt, which is 10. The slope is 10 in that case. Okay, so the voltage is going to take so much time, 1 second, to reach the same value of the current. This means the voltage is lagging. The voltage is not in phase with the current. So there is a phase difference when we use capacitors. Similarly, when we use inductor, we have the same equation, V is equal to something times the function of current. So whenever we have something like this, some A is equal to some constant times B, you change A, the C is going to resist the change in B. That's exactly what we had here. That's what we had here. That is what we have here. Okay. So in general, this is what it tells us, that when you change the current or voltage here, this component here will oppose the change of this component. In other words, if there is an inductor, the change in voltage will not immediately reflect the rate of change of current. Basically, it opposes the rate of change of current. It does not oppose the current itself, but the rate of change of current itself is what that is being opposed. So if you change the voltage, if there was a voltage source here and you flip the switch, it immediately will not result in an increase in current. The current will lag behind, like how the voltage lagged behind here, the current will lag behind. So in capacitance, the voltage is lagging behind, which means there is a phase difference between the current and voltage. In inductor, there is a phase difference between the applied current and the voltage. So there is always a phase difference whenever we use capacitors and inductors. But this is all the components we would use in a filter in an electric circuit, right? So if we want to remove particular frequency, then we would use, if you want to, let's say, remove DC component, you will use a capacitor, right? And that also comes from this expression. So with the rate of change of voltage is what that is affected. And when the frequency is higher, the rate of change is high. Frequency is lower, the rate of change is low. So the rate of change is directly proportional to the frequency of whatever signal that we are applying. So if our derivative is going to be higher, it means the rate of change is higher, which means the frequency is also higher. So for low frequencies, the derivative DC, let's say take DC current, the smallest possible frequency, okay, for which the derivative is 0 because it's a straight line, nothing is changing. So that's the smallest change in value. So if this is 0, the change in voltage is 0, then the current is 0. There is nothing that is going to flow through the capacitor. Okay, this is as good as saying that it is an open circuit. So that blocks DC. So this is the idea behind capacitor and inductor itself, right? So as the frequency increases, the rate of change increases, and you get a corresponding proportional current and or proportional voltage accordingly. So this is also going to introduce a voltage lag or a current lag, which means, coming back to our question, do the filters give an in-phase output? No, because the filters are going to be made with capacitors and inductors. So there is going to be an phase difference at the output. Now, how do we model this phase difference? How do we understand and analyze this phase difference? Only when we can understand and analyze, we can ensure that we can design filters such that the output phases are all aligned, and then you can synchronize the audio signal. So we need some kind of representation of these phases and magnitudes. Okay. And for this precise reason, we'll use complex valued signal, because the signals that are passing through in an electric circuit have different phases. We want to model them to incorporate these phase changes and magnitude changes, and these magnitude differences and phase differences. If we use real valued signals, we cannot do that, or it is not easy to do that. So we'll demonstrate that how real valued signals are very difficult to capture these things, whereas complex valued signals are easier. So how do complex valued signals actually model this? We'll use what are called as phasors.